Question 6. Anna is investigating the relationship between exercise and resting heart rate. She takes a random sample of 19 people in her year at school and records for each person their resting heart rate, H, beats per minute, and the number of minutes, M, spent exercising each week. Her results are shown on the scatter diagram. Interpret the nature of the relationship between H and M.
At this point, it might be a good idea to consider what a line of best fit may look like on this graph.
So in this one I can see that as M increases, H is decreasing.
And so my answer for part A, as M increases, H decreases.
Anna codes the data using the formula x is equal to log base 10m and y is equal to log base 10h. The product moment correlation coefficient between x and y is negative 0.897. Test whether or not there is significant evidence of a negative correlation between x and y. You should state your hypotheses clearly, use a 5% level of significance and state the critical value used. Okay, so we are looking at product moment correlation coefficient. Now the product moment correlation coefficient is equal to 0 to indicate no correlation between the sets of data. So my null hypothesis would be that my product moment correlation is equal to 0. I want to test whether or not there is evidence of a negative correlation. So my alternative hypothesis is to test whether the product moment correlation coefficient is less than 0. I've brought in an extract from my formula booklet. This table shows us the product moment correlation coefficients for varying levels of significance with different sample sizes. We are looking at a sample size of 19 and a 5% level of significance. Being careful to look for where these two values meet, I get a critical value of 0.3887. Now, in our formula booklet, this table only shows the positive values, but these are mirrored for the negative. So since we are looking at less than, our critical value is negative 0.3887. Now we're told that the product moment correlation coefficient between x and y is negative 0.897. This value is significantly less than the 0.3887, and since this is the case, there is evidence to suggest a negative correlation between these sets of data. Part C, the equation of the line of best fit on y is y is equal to negative 0.05x plus 1.92. Use the equation of the line of best fit of y on x to find a model for h on m in the form h equals am to the power k, where a and k are constants to be found. So we'll start from our h is equal to a times m to the power k, and we want to rewrite this so that we've got this log base 10m and this log base 10h. So let's take log base 10 of both sides. So log base 10h is equal to log base 10 am to the power k, and we're going to use our log rules to rearrange this right hand side. So the first log rule we're going to use is that log AB is the same as log A plus log B, so that can split this a and m to the k to get log base 10a plus log base 10m to the power k. And the second log rule we're going to use is that log a to the power k is the same as k log a. And so that's rearranging this log base 10m to the power k, which is the same as k log base 10m. Now we know log base 10h Anna has used to code y, and log base 10m is x. So we have written out h is equal to am to the power k in terms of the x and y that Anna has used for the coding. And if we bring down our equation of the line of best fit, the y is equal to negative 0.05x plus 1.92, we can now, looking at these equations side by side, equate the coefficients. So firstly, we can see that log base 10a is equal to 1.92. Using our calculator, 10 to the power 1.92 gives us a value for A of 83.17 and so on, which is 83.2 to 1 decimal place. And we can see that K must equal negative 0.05. Therefore, our equation for H can be written as 83.2 m to the power minus 0.05.